In this video, we're going to look at how to compute the area bounded by a function of y. So we mean a function defined as x equals g of y. A function like this takes each y value as an input and then produces an x value as an output. Note that a function like this doesn't have to pass any vertical line test because we just require that each input y corresponds to a unique value of x. In other words, there's just one x for each y value. And that actually means that a function of y would pass a horizontal line test. Now, when we talk about the area bounded by a function of y, what I mean is the area bounded between the y-axis and the graph of the function. And to get the area, we begin by visualizing a thin rectangular slice. This slice has a vertical location of y, just some arbitrary value of y, and then the length of the slice is given by the x-coordinate connected to that y, in other words, g of y. The height of that slice, that little differential height, is called dy. It's a small change in y. And this little slice has an incremental amount of area, in other words, a differential amount of area that we'll call dA. So to find the area of this entire region, we begin by writing down the area of this infinitesimal contribution to the area, dA. And dA has a width of x and a height of dy. Now we can write the width x in terms of y, and that's given by g of y. Now recall that integration is really a summation device for adding up infinitesimal contributions. So we can say the total area bounded by this curve is just the integral of dA. That literally means the continuous sum of all the dA contributions to the area. Then we just plug in our expression for dA. That's g of y dy. And the integral is entirely formulated in terms of a single variable y, so we can put the limits of integration on now. We're going to go from y1 to y2, the lower bound to the upper bound. And there's our formula for the area bounded by a function of y. To wrap things up, we'll work a quick example of computing an area bounded by a function of y. So we're asked to compute the area bounded by the y-axis, and the function g of y is equal to negative 1/2 y squared plus 2y on the y interval 0 to 4. And we can see in the picture that the curve actually intersects the y-axis at y equals 0 at the bottom and at y equals 4 at the top. So it's instructive to just go back to this idea of an infinitesimal rectangle every time. So there's a tiny slice of the area, and it's just located at an arbitrary vertical position y. That's connected to the length of the rectangle by the x-coordinate connected to that y value on the curve. And since x is given by negative 1/2 y squared plus 2y, that's the width of the rectangle. Again, the thickness of the rectangle is a small vertical increment dy. So we can immediately write down dA, the infinitesimal contribution to area given by our thin rectangle, and that's negative 1/2 y squared plus 2y dy. Again, the integral is a summation device. To find the total area, we simply add up all the contributions, all those dAs, and we already have a formula for that entirely in terms of y. So I end up with the integral of negative 1/2 y squared plus 2y dy. And because my integrand is phrased entirely in terms of one variable, I can put in my limits of integration. The lower limit is 0 for the starting value of y. The upper limit is 4. Now we just have to guess the antiderivative of this expression. And to get that done, we're using the power rule for antiderivatives. The antiderivative of y squared is 1/3 y cubed. So I have a negative 1/2 times 1/3 y cubed. The antiderivative of y is 1/2 y squared. Well, the 1/2 out in front will cancel the 2. So I end up with just plus y squared. And that expression is evaluated across the limits 0 to 4. Now the leading term here simplifies to negative 1/6 y cubed. And then I have a y squared, and I'm evaluating from 0 to 4. Before I just plug in the upper and lower limits, I notice that plugging in the lower limit gives me two terms that are 0. A shorthand notation for that is to just cross it out and say, well, that just gives me 0. So all I have to do is evaluate the upper limit. I have negative 1/6 4 cubed plus 4 squared. 4 cubed is 64. So I end up with 64 over 6, which is the same as 32 over 3. And then 4 squared is 16. I can multiply 16 by 3 over 3, obtaining 48 over 3. And negative 32 plus 48 is 16. So I end up with 16/3 for my area. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.